right, good morning, everyone. As Bill said, my name is Zach Vander Laan. The work I'll be presenting today is actually joint work with two of my colleagues who aren't here today, but I do want to acknowledge their work in this presentation. Today I'll be talking about and visually exploring some of the important applications of GPS trajectory data. So just to give a little background on this, this research effort began about a year and a half ago when the Maryland State Highway Administration purchased 4 months of GPS data from INRIX. Now, this was the first time they'd bought this type of data, so they reached out to University of Maryland CAT and asked us to help evaluate its use potential. So in the rest of this presentation, I'll kind of talk about some of the more prominent applications that we found of this data set. So this trajectory data set consists of a number of waypoints, which can be ordered in order to reconstruct routes taken on particular trips. In this visual on the left, we can see that we have 14 points, and the first point would be identified as the origin, while the 14th point would be the destination of that trip. And I should note that different data sets come in different formats, but in this case, we got raw GPS traces and had to actually do the map matching process ourselves. This data wasn't already snapped to the network. For each of the 20 million trips in our data set, we can identify the data source, so where it comes from, and also the vehicle weight class associated with it. Here's a little animation we made just to illustrate what this trajectory data looks like at a fixed location over the course of an entire day. So here, individual waypoints are shown with the white dots that are flickering all over the screen. And then the first and last waypoint in a particular trip are identified as origins and destinations and color-coded in green and red, respectively. So clearly, this GPS data we're looking at doesn't capture all of traffic. So one of the first things we wanted to understand is what percentage of actual vehicles on the road are we capturing with this data set. So in order to do this, we focused on 35 automatic traffic recorder locations where we have relatively accurate traffic counts at the hourly level. And by comparing real traffic volumes with those obtained from the GPS traces, we were able to calculate the penetration rate. And so here, this box and whisker plot shows the distribution of these penetration rates at the 35 locations, and we found the median value to be just under 2%. One thing each of the 20 million trips has in common is that at least one of the waypoints was recorded in the state of Maryland. Actually, about 75% of the trips are completely internal to Maryland, meaning they began and ended in the state. If we look over here on the right, we see that the median trip duration is about 18 minutes, and the median time between waypoints is about 1 second, which means our data is highly granular. I should note that by simply looking at this plot of the waypoints, we can't actually tell where trips begin or end. However, if we take the first and last waypoint in a particular trip and map them to their respective states, we can create a state-level origin-destination matrix, which can be nicely visualized with a chord diagram. So this is one way we tried to visualize an origin-destination matrix rather than just showing a giant Excel sheet. And the idea behind this is that this chord diagram is color-coded. So in this case, the state of Maryland is represented by the color green. So we can represent the trips taken that originate in Maryland and go to other states. In this case, because Maryland's green, the green ribbons represent trips from Maryland to, say, Virginia. And because Virginia's color-coded in purple, we can see that trips from Virginia to Maryland are indicated by this purple ribbon here. There are a couple of observations we can make that stand out from looking at this visually. First, we note that the trips going into Maryland and the trips going out of Maryland are roughly balanced. Additionally, by looking at where the particular trips go and come from, we see that most of the trips are to Virginia and Pennsylvania, DC, Delaware, so basically to neighboring states. If instead, rather than focusing only on the trips from Maryland to other states, we can look at the 75% of the data set that contains internal Maryland trips. So the main observation here, if we look at, if we basically create an origin-destination matrix at the county level within the state, we see that most trips begin and end at the same county. And this makes sense because, as I mentioned a few slides ago, the median trip duration is just 18 minutes. Rather than looking at the entire origin-destination matrix, perhaps we want to focus on a particular origin-destination pair of interest. In this case, this visual on the left shows Washington and Baltimore, and this may be our OD pair that we want to investigate. So in this visual, we've color-coded the direction of travel, just to highlight that we can do that. At this level of analysis, we could also look at traffic splits. Perhaps we may want to know the percentage of traffic that took I-95 rather than some other routes. And we can also look at the travel times and how they vary by hour of the day or perhaps day of the week. So here in this upper plot, we see a typical bimodal distribution where we see that the travel time is typically higher during the AM and PM peak period. So rather than focusing on origins and destinations, we can focus on one or the other. So in this case, we may be interested in only looking at the locations where trips originate. So if we look at, this is bouncing back and forth between two images, but if we look at the one with all of the waypoints plotted, it's kind of hard to see any patterns or see what's going on. But if we apply a simple linear heat map, we can actually identify that most of the trips are originating in a few concentrated areas, which are trip generators. Once we've identified important trip generators, there are some questions we can ask. One of them that we may be interested in is how far people travel within a certain amount of time, which are typically represented visually by isochrones or equal time contours. Now, there are a couple of interesting things about building isochrones with waypoints from trajectory data. The main thing I want to point out is that, or I guess the two things I want to point out are that first, this doesn't require any information about the road network, which typically you would need to construct isochrones. And also, it shows observed mobility patterns rather than how far you could go theoretically. Here I mention a couple, the general approach we've taken to build these isochrones. The first thing you have to do is get rid of anomalous waypoints because we do see some outliers in this data set. And so we've messed around with a few different approaches, trying to identify them through heuristics and also some density-based clustering. But in general, you basically get rid of the outliers and then draw these isochrones around the non-outlier points. So repeating this process at different times of day lets us see how mobility changes during peak and off-peak periods. So here I'm showing 4 important trip generators in Maryland, and and how this mobility is different during peak periods and off-peak. And we can see that during peak periods, people are able to cover less distance in a given amount of time. So rather than identifying analysis zones ourselves, which we saw by looking at states, counties, and cities, another application is to apply unsupervised learning and let the algorithm identify important origin-destination pairs. So one interesting way to apply this is to try to evaluate public transit routes. So the general idea here is that a transit system or the existing transit routes should generally reflect the origin-destination trips for which there's sufficient demand. So once you use some type of unsupervised learning algorithm to identify these important clusters, you can overlay the transit network and see whether the current transit system can facilitate these movements. Additionally, we can compare this GPS data to other data sources. So just in this simple example here, we're looking at an EPA measurement location in Maryland, located right next to I-95. And at this location, we're counting the number of GPS vehicles that are passing through, and then also comparing those values to two types of emissions reported by the EPA. So the general idea here, which we haven't actually implemented, is that perhaps you can use these GPS counts, as an input to try to predict emissions or perhaps some other sparsely located measurement quantity elsewhere throughout the state. And actually, the application of this idea that I want to touch on before wrapping up is using these GPS counts to try to estimate traffic volumes throughout the state. So the main impetus for this is the fact that transportation agencies would really like to know the traffic volumes, at the hourly level throughout the entire state road network, but currently only have volumes at about 2% of them. So the main idea here is if we can take a set of automatic traffic recorder stations where we do know the traffic volume and try to build a model which takes in inputs such as speeds, the road infrastructure, the weather, time of day, and also includes the GPS counts, can we build a model that allows us to develop this relation between these input variables and the traffic volumes. And so then once we build this model, assuming it's sufficient, and we have the inputs everywhere throughout the network, we can then go apply this model to places where we don't have volumes. And so I'm not going to get exactly into some of the preliminary results we've generated, but one question that would likely come up is how would we validate this type of model, because we don't have traffic counts at other places in the network. So to do this, we're basically doing some type of repeated cross-validation procedure where we train the model on all but one of the test stations and then try to predict the volumes at that one remaining station and then repeat that a number of times. So by doing this, we can predict the traffic volumes at all of these stations. And this graphic here is just meant to point out that the top two are kind of the normal station behavior where the predictions are generally pretty decent, but there are cases, as shown by this one in the lower left, that are particularly poor, and a few that are excellent. So overall, though, this estimation performance is highly dependent on the model inputs, the penetration rate of the GPS counts. Currently, one of my colleagues is working on using a multi-layer neural network and some applications of deep learning to try to improve the model performance. But overall, this is about what I wanted to summarize, just some of the key applications that transportation agencies may be able to use this GPS trajectory data for. Overall, we're pretty excited about its use potential, and I also should point out that the CAT Lab, which is part of our CAT organization, is currently developing this suite of tools to try to make some of these analysis procedures easier for individuals to use. And that's all I have. I just want to again thank the other researchers who couldn't be here today to present our joint work, and also thank the Maryland State Highway Administration for purchasing this data and supporting us through the process. Thank you.